Good morning. There it is. Good morning, everybody. It is Monday. It's sunny today. Last week was a little dreary, unfortunately. Good morning, Aurora, Joey, Brain Fog, JR. Welcome to another week. You guys are surviving, finishing things out. I got lots of questions on the programming project this weekend, which was great. I've been really impressed with you guys for the programming project. Morning, Joey. I really have. I've been really impressed with you guys for the programming project. Every time I get a question, it's usually following code that you guys have already written, which is awesome. So you'll be like, hey, this doesn't work, but I tried it. Which that's not always the case in the past, and I don't know if the programming project is just maybe a little easier to understand this year, or if the videos have been really helpful. But I've been really impressed with you guys. It makes me really happy. You know what, Matt? That happens. You're done with your midterms though, which is good. Which is good. I mean, it also could be your definition of behind. Halfway through B, okay. You're getting somewhere. Remember, everybody, if you get stuck on something, move on and come back to it. Sometimes you just need a break. And I would hate for you not to get some points because you got stuck on something and couldn't move on to something else. Yes, after C, things do move a lot faster, which is good. That's the way it was more or less designed. So you can always write D and E without finishing A and B and C, because you know essentially what those should look like, or have an idea about what they look like. Yes, JR, that's a really good idea. So that's why I do give you guys the rubric, so you guys can more or less see where the points are. Like I said, I would hate for you guys to lose points because you got stuck on something and didn't move on. I know it's really hard, at least for me. I'm very much a perfectionist, and it's really hard for me to kind of forget about something if it's not complete, and I completely understand that. But sometimes you really do need to play the game of school a little bit. Yeah. The homework. What does the homework look like? Let me check and see what the homework looks like. I totally forgot. Homework, 11? Homework 11? Homework 10? Homework 11? So the first step when solving any of these systems is to write it in the form of AX equals B. So the comprehension quiz, it's not broken. It works. I just checked it. It's a lot of steps. Joey, I don't know what you mean by part 2, like problem 2? Oh, good lord. Oh, okay, so for the homework, you're doing a bunch of determinants. I'll just talk about this for a little bit. Yeah, you can always retake the quiz, Aurora. You can always retake the quiz. Think about the quizzes as... the goal of the quizzes is for you guys to learn. I don't care when you do them. You can, if you lose points on some, you can always go back and get those points back. The goal is for you just to learn through them. That's really it. So, yeah. Okay, so let me talk a little bit about the homework. So the homework, you're finding a bunch of determinants for problem 1. It's just using cofactor expansion. Yep. For problem 2, you're using your determinant properties. So when it says find the determinant by row reduction to REF, you're doing Gauss elimination. So there's big matrices there, but once again, it's just practice. I totally forgot you had a 4x4 and a 5x5. Check your work with MATLAB, but you're just doing Gauss elimination, and then you're gonna use the triangle matrix property in order to find the determinant of your lower triangle row echelon form matrix. And that's it. That's it. So it's just more row operations, which we're gonna do more of. We're gonna do more of this week. But this week, today, I'm gonna show you exactly the row operations we're gonna apply every single time. Let's see, problem 3, you're just doing Cramer's rule. So once again, more determinants, more determinants, which the determinant is really important. The idea that if the determinant is 0, that means our matrix is not invertible, means it's singular, means the inverse doesn't exist. All of those are really important key concepts, and we will get more into those next week and why we care about that. But it's really just calculating a bunch of determinants. Okay. Nice to know there's a good PDF. I'm assuming you're talking about the notes? Anyway, okay, let's go ahead and get started. Hopefully, after the end of today, the quiz will make a little bit more sense, and we'll know all of our steps. So let's go ahead and there's a lot of steps. So let's go ahead and start. Okay, notes. There we go. So this week we are talking about what's called PL or LU. Today is going to be LU factorization. When we say factorization, we're literally finding the factors. So when you say find the factors of 6, it's going to be, oh my gosh. This. I like my royalty-free playlist list. Sometimes. So find the factors of 6. It'd be 1, 3, 2, 6. Essentially, what can we multiply? What numbers can we multiply by in order to get 6? We can multiply 1 times 6 or 3 times 2. Same thing with a matrix. We're figuring out which matrices we can multiply together in order to get A. In this instance, we are finding specific matrices, one being a lower triangle matrix and one being an upper triangle matrix. So L is going to be a lower triangle matrix. That's why it's called L. And it looks like this. Wrong one. L looks like that, where we're going to find numbers for L21, L31, and L32. And U is an upper triangle matrix. And it looks like this. This might be some of my neater handwriting. So that is what L and what U are going to look like. So if I multiply L times U, then I'm going to get A. Okay, so the key thing for this is figuring out how to get L and how to get U. The way we're going to do that is by following these steps. So we're going to apply only row operation 3. So remember, row operation 3 is where we're going to take a row. We're going to take a row and multiply or add that row to some non-zero multiple of another row. So remember, this needs to be a 1 and this needs to be a 1. Okay, we cannot multiply the row we're replacing by a number. Okay, so there are, for a 3x3 system, we have 3 row operations we're going to apply, which you will have to do a 4x4 in your homework, but that's just practice. For a 4x4, you have 6 row operations you'll need to apply. And then for the exam, it'll be a 3x3. Okay, so these are the row operations we're going to apply. We're going to take row 2, and we're going to replace row 2 by adding it to some multiple of row 1. And then the second one is going to be replacing row 3 terrible R, by adding row 3 to some multiple of row 1. So those are our first two row operations. And then we're going to take row 3 and add it to some multiple of row 2. So we're going to do this one first, then this one, then this one. That's it. If we do those, essentially we are applying Gauss elimination just with the same 3 row operations every time. If we do those, we will end up with U, and then we can use what's called our multipliers, these numbers here, in order to put together our L. Okay, so let's go ahead and do this. Okay, so first thing, we're going to take row 2 and add it to multiple row 1. The goal is to make this a 0. So I'm going to take row 2 and add it to row 2 plus negative 4/3 row 1. So I need to multiply row 1 times 4/3, which if I do that, I end up with negative 20/3 and 8/3. When I add those together, I'm not going to say A, I get row 1 doesn't change, row 3 doesn't change, and row 2 now becomes 4 plus negative 4, or 0, 1 plus negative 20/3, yes, 1 plus negative 20/3, which is negative 17/3. Whew. Thought I messed up already, but 3/3 minus 20/3 is negative 17/3, and then 1 plus 8/3, which is 3/3 plus 8/3, which is 11/3. The only downside to, or I guess one of the downsides to LU factorization is the fact that we are more likely and will probably see fractions, because we have to apply only row operation 3, so just keep that in mind. But honestly, just check your work in MATLAB. Okay. Okay, so now my second one is going to be row 3 plus some multiple of row 1, which is going to be making this a 0, which means it's going to be positive 4/3 row 1. So row 1 times 4/3 is going to be 4, 15, nope, 20/3. I just did this. And negative 8/3. So when I do that, I'm going to end up with row 1 doesn't change, row 2 doesn't change, row 3 now becomes negative 4 plus 4, which is 0, negative 4 plus 20/3, which I will go to my work, 8/3, and then 5 plus negative 8/3 is 7/3. And then my last row operation is going to be row 3 equals row 3 plus some multiple of row 2 to make this a 0, which that multiple is going to be 8/17. So those are my 3 row operations. When I do that, I end up with 3, 5, negative 2. Row 1 doesn't change, row 2 doesn't change. And then row 3 now becomes 0, 0, and then I end up with 11, nope, let me write this out. 7/3 plus 8/17 times 11/3. If you do that, it ends up with 69/17. So once again, downside, you'll have to do the fractions, finding common denominators, all of that fun stuff, but you have a calculator, you have MATLAB, you should be able to check your work. Those are my 3 row operations. So notice I end up with my lower triangle, just like I did using Gauss elimination. Just so happens I use the same 3 row operations every single time, regardless of the matrix. Row 2 equals row 2 plus some multiple of row 1. Row 3 equals row 3 plus some multiple of row 1. Row 3 equals row 3 plus some multiple of row 2. Every single time. Woohoo, great. Okay. Once I have that, this answer down here ends up being my U, my upper triangle matrix. So note, it looks just like this. So I found one of my matrices. Awesome. That's a really good question, JR. So I found the 8/17. Essentially, you can always find what this multiple is going to be by taking the number in, so I need to take, so I need to find -17 thirds plus, or times something, plus 8 thirds. I need that to be equal to 0. So this is essentially, let me rewrite it. Essentially, I can write that as an equation. So if I want this to be a 0, that means I need to take 17 thirds times x, times a number, plus 8 thirds equal to 0. So in order to find what that x is going to be, what this number is going to be, it's going to be x equals -8 thirds divided by -17 thirds. So it's this number divided by this number every single time. Notice for this first row operation, using this matrix, it was this number divided by this number. For my second row operation, it was this number divided by this number. For my third row operation, it was this number divided by this number. So you can always take the number you're trying to make a 0 divided by the number you're going to use in order to do that. The steps always lead to zeros. Yes, so essentially your goal is to make zeros, so you should end up with zeros. We are essentially doing Gauss elimination, so we want those to be zeros. And yes, so JR, the nice thing about LU factorization is it's algorithmic. It is the same things every single time. You just do this process every single time, regardless of what numbers you have in A. Take this number, divided by this number, do the row operation. Take this number, divided by this number, do the row operation. Take this number, divided by this number, do the operation. Every single time. So that's one of the nice things about LU factorization is it's you just blindly do the steps. Which the nice thing is you can do this for Gauss-Jordan too. If you want to, you can always do these steps for Gauss-Jordan elimination as well. So if you come to the exam and you're like, I don't want to have to think about which row operations I need to do, and I want to just apply the same ones every time, you can apply these same ones every single time. So LU factorization essentially is the same as Gauss elimination. It just so happens our end result is a little bit different. In Gauss elimination, we're really just interested in whatever our result is here. For LU factorization, we take it a couple steps farther. And a couple steps farther, I mean, what we're going to do is we also need to find our L matrix. So our L matrix looks like this. So I'm going to copy and paste this down. Copy. Paste it down. Move it up a little bit. So my L matrix looks like this. My row operations. But L21, L31, and L32 come from these values. It's going to be the inverse of those values. So L21 is this number used to make our first elimination, make our first 0, except we're going to change the sign. And the reason for that is because, I can tell you the reason. Because essentially what we are doing through this process is we are multiplying our matrix, our A matrix, by a bunch of elimination matrices. An elimination matrix, for, if you don't remember from the videos, is our identity matrix. But for an elimination matrix, this number appears in the same location that we made a 0. So essentially, if there was a number, if we end up with a 0 here, then that is exactly where our eliminator, our elimination, our multiplier, there we go, that's what it's called, our multiplier shows up. Where this matrix is our elimination matrix, and just so happens, I'll call it L21, because it's used to eliminate the 0 in row 2, column 1. Essentially, this is the matrix that does this row operation. So if I took A, and I multiply it by L21, I would end up with this matrix. So this elimination matrix, I'm not explaining this very well at all, but that's okay, these steps still apply. This elimination matrix does the row operation. So if I do L21 times A, it does the row operation. So in MATLAB, this is one of the ways where we can apply this process. I can put together this elimination matrix, say L21 times A, and it will do that row operation. It will give me the 0 here in A. Let me clean these things up. Same thing for this one. My elimination matrix here, L31, looks like identity. But now this number, 4/3, shows up in the 3-1 location. I made this a 0, it shows up in that same location. So now if I say A, L21, L31, now if I do multiply all of these together, first it's gonna make that 2-1 elimination, and then it's gonna do that 3-1 elimination. Make this one a 0. So what that means is that L, our final L matrix, is essentially composed of all of these elimination matrices, and it's the inverse of all my elimination matrices. So L at the end of the A is going to be L32 inverse times L31 inverse times L21 inverse. And fundamentally, all you guys need to know is that each of these multipliers that we used to put together, or to do our row operations, what you're gonna do is you're gonna change the sign and put them in one at a time. So the first one, to make our first 0, shows up here, and it's gonna be positive 4/3, because I changed the sign. Negative 4/3 becomes positive 4/3. For my second one, L31, it's this number here with the sign change, so it's negative 4/3. And this one here, my last one, is 8/17 with the sign change, so negative 8/17. Hold on. I have a sign, negative 17, negative 17. Yeah, nope. I probably wrote something down incorrectly. Yeah, we're good. We're good. Thought I had a sign change. Okay. So you can think about it in terms of our elimination matrices. That's more confusing to me, I'm not gonna lie. Like I said, I understand why I did not do a very good job explaining it. I have sat there and I have delved deep into LU factorization and all the fun stuff. But at the end of the day, you're just gonna take these numbers, change the sign, put them inside of L. So that we end up with U, and we end up with L. Yeah. Where if I multiplied U times L, or L times U, sorry, L times U, I would get A back. So here's U. U looks like this. 3, 5, negative 2, 0, 17/3, 4, 11/3, not 4. And then 0, 0, 69/17. And here's L. If I do this multiplication, I should end up with A again. And note, if I do row 1, if I do row 1, column 1, I end up with a 3. Plus 5 4/3, 5 times 4/3. Oh my goodness, that's not, this is L. These are backwards. I was like, wait a minute, that's not working. There we go. L times U. That makes way more sense. If I do row 1, column 1, I end up with a 3. Row 1, column 2, I end up with a 5. Row 1, column 3, I end up with a negative 2. Which is my first line in A. And then row 1, row 2, column 2, I end up with 4. Row 3, column 1, I end up with negative 4. And then same thing, these other two get a little more complicated because there's more terms to multiply by, less zeros. But I would essentially get A back. So this is one way to check your answers. You can also type in these matrices to MATLAB and confirm that that's what you get. Okay, so that is our first way to find L and U. We do those row operations, same ones every single time. Another way we can find L and U is using the fact that we know L is supposed to look like this and U is supposed to look like this. If we keep those matrices in their variable form and do the multiplication, it ends up like this. So this is in your guys' table, but no, you can always find it using matrix multiplication. So row 1, column 1, you're going to get U11. Row 1, column 2, you're going to get U12. Row 2, column 3, you're going to get U13. Row 2, column 1, you get U21 times U11. The rest are zeros. Row 2, column 2, you get L21 times U12, and then plus 1 times U22, or this equation right there. Row 2, column 3, L21 times U13 plus 1 times U23 plus 0 times U33, or this equation right here. Once you do all of those matrix multiplications, you know that that should equal A. So you can use, essentially, equal matrices in order to solve for all of these unknowns. So we know, let's say this is our A this time. This should equal A. 3, negative 5, 2, 5, 4, 3, 2, 5, 3. So equal matrices tells me that U11 equals 3. U12 equals negative 5. U13 equals 2. So no, row 1 doesn't change. A, the first row in A is always the first row in U. Every single time. Okay, if we move on to the second row, L21 times U11 equals 5. So L21 times U11 equals 5. U11 is 3. I found that up here. So L21 times 3 equals 5. So L21 equals 5/3. Same thing moving over. L21 U12 plus U22 equals 4. U12 equals negative 5. L21 equals 5/3. So we have 5/3 times negative 5 plus U22 equals 4. And then we solve for U22. U22 ends up being, for this matrice, 37/3. Once again, we're dealing with fractions. Not always the nicest, but that's okay. I'm going to box all these numbers because we will need them. And then moving over, L21 times U13 plus U23 equals 3. Once again, L21 is 5/3, U13 is 2 from up here, plus U23 equals 3. If we solve for that, it ends up with U23 equal to negative 1/3. And then we keep moving. So now we have our last row. So every single time, essentially, the point is every single time we have something from our LU matrix, something from our A matrix, and we can solve for our remaining unknown. So this one says L31 U11 equals 2. U11 equals 3. So I have L31 times 3 equals 2, or L31 equals 2/3. So here we're not even doing our row operations. We're just using equal matrices. And this method is fine. Either one should give us the right answer. The next one, L31 U12 plus L32 U22 equals 5. Okay, 2/3 times -5 plus L32 times 37/3 equals 5. L32 is my unknown, and that should end up being 25/37. And then my last one, L31 U13 plus L32 U23 plus U33 equals 3. So this equation and this number. Plug in all of my known values. So 2/3 times 2 plus 25/37 times -1/3 plus U33 equals 3. U33 ends up being, for this matrix, 70/37. So once you find all of these pieces, then you just plug them in to your matrix. So you know U looks like this, you know L looks like this, you know what all of your numbers are, so you just plug them in. So L ends up being 5/3, 2/3 and 25/37. And then U, so here's L, and U ends up being this, 3, -5, 2, 0, 37/3, -1/3, 0, 0, 70/37. So you just plug it in. And this is another way where you can find L and U. Once again, if you do this multiplication, you should end up with A. What do you divide? So, Joey, your question, will we have access to MATLAB for the final exam? It was mentioned in our last instructors meeting, potentially using Respondus Lockdown Browser. I'm not overly fond of this idea, but it is a possibility. I will have more information on that on Thursday. So it may be either at this point in time. I told you in the past you should have access to MATLAB because up until last Thursday, the plan was always for you guys to have access to MATLAB on your final exam. But someone mentioned it in the instructors meeting, so we are going to decide on Thursday. I will have more information on that next week. What do you divide R1 and R2 by to solve for L in the beginning before doing the row operation? I don't know what you mean by that 10,000th sheep. I don't know what you mean by that 10,000 sheep. Like, how do you find your row operations? That's a very good question, Matt. Very good question. Like I said, I'm not in favor of it, but I can't make all the decisions, so we will have all of those decisions made. We'll look at the pros and cons and all that fun stuff. And I'll get back to you next week. Okay, so we find A and we find L and we find U. I'm trying, Matt. I really am. It's hard. At some point in time, you do need to learn this stuff and you do need to practice. But my goal is to make it manageable for you. Okay, so we find L and we find U. Yay, woohoo, we can do that. That's great. That's all fine. That's fun and dandy. But really the goal is to solve our system of equations. So let's say that we have a system of equations with, this is our A matrix, which it's the same A matrix we just found. So here's our L and here's our U for that A matrix. And let's say that this is our B vector. 7, -12, and -17. So using LU factorization, essentially, the goal is that we've broken A down into two matrices, L times U.
So really, if I rewrite the system, it's, nope. If we rewrite, wrong button. If we rewrite the system, it essentially looks like this. So here's the LNU I just found. Here's my X. And here's my B. Notice I have a upper triangle matrix and a lower triangle matrix. One of the reasons why we used Gauss elimination was so that we could easily solve our system equations, because when you have an triangle matrix, what you can do is you can rewrite your system so that you have one unknown in one equation, two unknowns in another equation, and three unknowns in your last equation. So breaking it up into L and U, essentially we have that same idea. There's a couple more steps, but we have that same idea. So what we're going to do is we're going to break this system up into two different systems, where I'm going to take out U and X. Literally, I can do that. So I'm going to take out U and X. I'm going to move it down. And I'm going to set it equal to some Y values. So that means that essentially I am replacing U and X by Y. So now I have two different systems. I have Ly equals B, and I have Ux equals Y. So what we're going to do is we're going to use this system here to solve for our Y values. Once we know our Y values, we can plug them in and solve for our X values. Okay, so let's go ahead and do that. Here we can see this first equation. We see that y1 equals 7. Woohoo, we did that. So y1 equals 7. Cross off all my extra lines. This second equation tells me that 5/3 y2 plus, or y1 plus y2 equals -12. If I plug in my 7 here, then it's going to tell me that y2 equals, I can do this, -71/3. And then this last equation here tells me that 2/3 y1 plus 25/37 y2 plus y3 equals -17. Plug everything in. 7, plug in my -71/3. And this will tell me that y3 equals -210/37. So some fun numbers. Zoom out a little bit so you can see it all. Okay. So I just broke it up into two different things. I broke it up into two things. I first rewrite it as Lux equals B. I take out Ux, make it Y. Solve for Y. Essentially, I'm just doing it in two steps. Solve for Y. Then I can plug in my Y values down here. And using my Y, now I can solve for X. So once again, this is another lower triangle matrix. So this tells me that 20/37 x3 equals -210/37. This tells me that x3 equals -3. At least it should. Um, 10,000 sheep. I had a Wi-Fi issue on one of my exams for my other classes. What's the policy for this class? So, I don't know. What would happen if your Wi-Fi went out? Yeah, I know, JR. That doesn't look right to me either. But, so, just a question. What happens if your Wi-Fi goes out when you have Respondus Lockdown browser?
What we do here is
Fire alarm goes off. Leave like you should. And I will give you extra time. Can't believe that happened during the midterm. And I can't believe... Oh my goodness. I'm so glad I let you guys have your microphones turned off. I can't imagine listening to a fire alarm while your midterm's going. So what happens if your Wi-Fi goes out in the middle of like an exam that you're taking with Respondus Lockdown Browser? Like, Aurora, I know there's some people that have that issue. Okay, hold on. 70, there we go. This is supposed to be 70, that's not a 20, that's a 70. That's why. Can't read my own handwriting. That's much better. That makes sense. There we go. There, that's where it is. Okay. Okay, so if we keep solving this, then the second equation tells us that 37 thirds x2 minus 1/3 x3, which is negative 3, equals negative 71 thirds. This tells me that x2 is negative 2, which makes sense. And then this first equation says that 3x1 minus 5 times negative 2 plus 2 times negative 3 equals 7, or that x1 equals 1. And there we go. I've solved my system of equations. Okay, so those are the steps. Those are our steps. Let me write them over here. Given a system of equations. So note if I rewrote this system of equations, it would look like this. 3x1 minus 5x2 plus 2x3 equals 7. And then 5x1 plus 4x2 plus 3x3 equals negative 12. 2x1 plus 5x2 plus 3x3 equals negative 17. So given a system of equations, here we go, we have our nice little system. First, we need to write it in the form of ax equals b. That's always your first step for pretty much everything. If you're not given it in the form of ax equals b, write it in the form of ax equals b. Then we need to find L and U. So we need to break A up into L and U. So we're going to do our 3-row operations. We're going to say row 2 equals row 2 plus some multiple of row 1. We're going to say row 3 equals row 3 plus some multiple of row 1. And then row 3 equals row 3 plus some multiple of row 2. Once we have L and U, so this will give us U. This ends up with U. L is constructed. So L is composed of all of these values. So find L. Once we have that, we can write our system in the form of LUX equals B. You have to do them in this order. I mean, you could technically switch those two around if you want to, but you have to do these two first, and then do this one. You have to make these give you zeros in your first column. This gives you a 0 in your second column. Obviously, this is for, I shouldn't say obviously, but this is for a 3x3. If you had a 4x4, you would do the same steps. You would just have more of these row operations to do, but the same steps would apply. Once you have LUX equals B, once you rewrite it in that form, you're going to break it up. So you're going to break up into LY equals B and UX equals Y. Then you can solve for Y and then solve for X. That's 9 steps. I'm pretty sure that's exactly how it's phrased in the quiz. But from start to finish,
Using LU factorization in order to solve a system of equations, this is what you do. It's the same steps every time. You're doing 3 row operations, and then you're just solving 2 systems with triangle matrices. Okay, so we've got, and it's confusing on the quiz because in the notes, I don't show you how to do everything together. In the notes, I tell you how to do this, and then I tell you how to do this. It's 2 separate things, but together it looks like this. So if you have to solve a system of equations from start to finish using LU factorization, these are the steps you apply. Okay, so that's what it looks like for a 3x3. For a 4x4, it's the same thing like I said. We find AX equals B, we find L and U. We just have more row operations. Once we have L and U, these things still apply. We just have a bigger L and a bigger U. So let's look at a 4x4. You'll have to do that in your homework. So here's a 4x4. So first, I'm going to find a 0 here. So I'm going to say, pull up my answers so that I don't have to worry about math errors. Yeah, okay, so let me talk about that before I get to the 4x4. So the reason why we break it up into, so L looks like this. That won't erase. L looks like this. And U looks like this. Every single time. X looks like this. And B looks like this. This is essentially what we have. These 2 multiply to create A. Here's my X, and here's my B. AX equals B. And we know multiple ways to solve a system in the form of AX equals B by now. That's not really the point. The point is that we're showing you all of these different ways, and they all have pros and cons. One of the pros about breaking things up into L and U is that it gives us, so we only do 3 row operations for a 3x3, same 3 row operations every single time. So it's a very much defined process. It's very algorithmic. It's easy. Essentially, if you understand it well enough, you could write your own script file. You could write your own code that does this. In fact, I wrote a beautiful function that shows me all of my work and everything. But what it does is it breaks things up into 2 triangle matrices, a lower triangle matrix and an upper triangle matrix, which we know that it's easy to solve a triangle matrix. If I write my system of equations for a triangle matrix, whatever our matrix looks like, I can easily see that this last system says 6z equals 12. I can solve for z. This one easily tells me that 4y plus 5z equals 11. I know what z is now. I can easily solve for y. And then same thing here, x plus 2y plus 3z equals 10. Obviously, basic example, terrible handwriting. But I can easily solve for z. Once I have z, I can easily solve for y. Once I have y and z, I can easily solve for x. So we know it's easier to solve a system of equations when we have a triangle matrix involved for A. So that's some of the idea behind this LU factorization. There are probably some other linear algebra properties that we get by breaking up A into L and U. Later on, next week, we're going to get to eigenvalues and eigenvectors, and we'll get to diagonalization, where we're essentially decoupling our A matrix. So our L matrix probably gives us some inherent information about A or our system, and U also probably gives us some inherent information about our system. That's beyond my knowledge. I am not a mathematician, but there's probably some properties we can pull out from L and U.
Give me 2 seconds. Forgot to shut my door. But what we can do is we can use these matrices in order to break up our system into 2 different systems with triangle matrices for each system. So what we do is we take out ux and we substitute it with y. So if I take u times x, if I do this multiplication separately, I'm going to end up with a single vector of values. And we'll call that vector y. So essentially, if I have ux in here equals y, essentially I'm just replacing that with a different variable. So I'm replacing this with a different variable called y. It's just a vector. And now that becomes my unknowns. Let me erase that now. And this becomes another set of unknowns that I can solve for using L and B. I'm just replacing ux with y. So now I have a system of equations that has a triangle matrix, my unknowns, and my b vector. So using this, I can easily solve for my y values. I can solve for what ux equals. Once I have that, then I can solve my second system of equations, ux equals y. And now my x are my final unknowns, u is another triangle matrix, and I can easily solve for my x values because I have another triangle matrix. So we're just doing it in 2 steps. It's always the same 2 steps. It took me a while to figure out, oh, okay, ux, we're just taking that out and replacing it by a variable. Because it's not always intuitive with matrices. It really isn't. Okay, so with our remaining 2 minutes, let me go through the process quickly on how to break up a 4x4 into L and U. So our same goal is to break it up into L and U. L looks like this. Nope. So L is still going to be a lower triangle matrix. U is still going to be an upper triangle matrix. U11, U12, U13, U14, 0, U22, U23, U24, 0, 0, U33, U34, and then 0, 0, 0, U44. So it's still going to look like this. You can do that matrix multiplication like we did here and solve for it using equal matrices. Or you can do your row operations, which is the same row operations every single time. For this one, it's going to be row 2. I can do this. Row 2 equals row 2 plus some multiple of row 1. Row 3 equals row 3 plus some multiple of row 1. Row 4 equals row 4 plus some multiple of row 1. So for this matrix, this multiple here is going to be, to make that one a 0, is going to be 1. This multiple here for that matrix is going to be, where's my work? There it is going to be negative 2. And to make this one a 0, it's going to be 1 again. Once I do all of those row operations, I end up with this matrix. Negative 1, all my zeros here. So here's my first set of multipliers. In order to fill L, I just negate the sign. So this becomes negative 1, this becomes 2, and this becomes negative 1. Then I move on to my next set of row operations, which it's going to be the same every time.
And we replace row 3 by saying row 3 equals a multiple of row 2. And then row 4 equals row 4 plus a multiple of row 2. For this matrix, to make these two zeros, I'm going to use 3/5 and -6/5. It's always going to be this number over this number and then this number over this number. If you remember from our 3x3, it's always that same set of numbers. Once I do that, I'm going to end up with another matrix with these as zeros. I don't want to write it out. So many numbers. 0, 0, -16/5 and 16/5, 0, 0, 7/5, 13/5. So ultimately we can solve all the, yes, that's essentially what you're doing. So you're finding all the L values in your first column, and then you're moving on to the L values in your second column. So the second column, it's -3/5 and +6/5. It's these numbers with the sign changed. And then we move on to our last row operation, which is going to be row 4 equals row 4 plus some multiple of row 3. So it's the same steps every single time. So for this matrix, it's going to be this number over this number, or 7/16. So when I plug that in, it's going to be -7/16. There's my L. Once I do that row operation, that result is going to give me U, which if I write it out, and then 4. Oh, that becomes a nice number. There we go. So you're essentially just doing Gauss elimination, but you're applying the same row operations every single time. You're going to find all of your L values for your first column, find them all for your second column, find them all for your third column. Take row 2 minus or equals row 2 plus some multiple of row 1. Row 3 plus some multiple of row 1. Row 4 plus some multiple of row 1. Then row 3 plus some multiple of row 2. Row 4 plus some multiple of row 2. And you would continue this. So note, in order to find your zeros in column 1, you always use row 1. In order to find your zeros in column 2, you always use row 2. In order to find your zeros in column 3, you always use row 3, etc. Okay, we are past time, we are out of time, but this is LU factorization. Once you have your L and your U, go back to my steps, here they are. Once you have your L and your U, you break it up into LUX equals B, then you separate them, LY equals B, UX equals Y. Okay, that's it for LU factorization. On Wednesday, we will get into PLU factorization, which is essentially just LU factorization. We just also do row swaps, and there's a reason for that. I'll talk about that on Wednesday. But yeah, I will see you guys on Wednesday. If there are any final questions, let me know. If not, have a great day. Great week. You're almost there. You're almost there. I'm going to jump over to office hours. I will see y'all later.